Friends, one of the most promising technologies that have been promised to us for several years now is self-driving cars. One of the key components of that technology is the vision piece. The self-driving cars need to understand the visual world in terms of lanes, in terms of pedestrians, in terms of other cars. But there's real challenges here. I'm going to suggest that there is a reusability principle at the core of the problem of computer vision. And this principle can be used to jump forward and produce vision systems that can actually produce self-driving cars. I want to start by demonstrating the urgency of this question. More than 40,000 people die every year in the United States in traffic fatalities. That number is going up rather than down in recent years. It's pretty controversial to say that when we get real self-driving cars, this number will be dramatically reduced. The robot drivers will not get distracted. They will not get drunk. They don't get tired. And therefore, they will commit many fewer mistakes than human drivers. So this is an urgent question and technology problem that we should be waiting expectantly for and asking what the holdup is. As you all know, Tesla is one of the pioneers in self-driving cars. But the Tesla cars really aren't there yet in terms of self-driving. One of the reasons is that the computer vision systems aren't good enough yet. Here is an incident that happened recently where a Tesla car was in self-driving mode and crashed into a police car on the side of the road. The police car itself was responding to a car crash. It seems like it should be pretty easy to recognize a parked police car. It's got flashing lights, it's got special coloration and symbols. But the Tesla vehicle couldn't do it, and that led to an incident. Fortunately, no one died in this incident, but it's still a real discouraging sign about self-driving cars. Now, I do want to say that there are two approaches to self-driving autonomy, the Waymo approach and the Tesla approach. The Waymo approach is in some sense an easier problem because it assumes that we have another sensor component, which is the LiDAR. So you can see on the Waymo car, there is a contraption on the top that is LiDAR. And LiDAR is really nice because it tells you if there's something in front of you. So that makes it a lot easier to notice if you're about to crash into something. Tesla depends only on vision. Tesla made a commitment to pure vision-only autonomy. The rationale is that humans don't need LiDAR to drive, so why should robot cars? We should be able to program the robots to drive as well as humans do. Now you can see in this image why that's such a hard problem. Here is a pedestrian who's about to get hit by a car, and really only the lower half of their body is illuminated. The upper half, I think they're wearing a dark jacket, so you can't really see it in that lighting. Clearly, computer vision is a hard problem, and we need to use the best technology we have to solve that problem. Now, I want to claim that the holdup and the delay in computer vision for autonomous cars is because they're using an old approach to machine learning. And I say old, I just mean it's not the most new and the most modern approach, it's the approach that defined the early era of machine learning. In this approach, it's totally based on labeled training data. Let's say you want to detect cats in images. What you do is you have human annotators sit down and mark thousands of images as cat or no cat. That produces a labeled training set of label image pairs. X is the image, Y is a label. Then you run your statistical algorithm and you produce a probability model of the probability of an image given, the probability of a label given the image, the probability of a cat in a specific photo. Now, there's something that's important to notice, which is that the amount of data you can use in this approach is pretty limited because each label requires some human effort to create it. You have to have someone sit down and mark these images, depending on whether they contain a cat or not. The second thing to notice, and this is a little bit subtle, but the label is actually a very thin slice of data. It's not very bulky itself. It's just a true or false. You can imagine different versions, the labels are a little bit more substantial, but basically it's a thin data object. Now that's important because of this fundamental limitation of classical machine learning, which is illustrated by these graphs. The deep problem of classical machine learning is overfitting. What this means is that if you have a limited data set and you propose a very complicated model to describe it, that model won't generalize to future observations. So this graph in the center is a good balance between pretty decent accuracy and a simple model. The curve is pretty simple. Whereas on the right, you have a model that has overfit because it's proposed a very complicated curve that goes through all the data points and achieves good accuracy, but it will not achieve good accuracy on new data points that represent future observations. Now, a lot of people have talked about how to formalize this notion of overfitting. One simple way to do it is to talk about the data volume being modeled. So in this classical approach, we had 10 or 20 or 100,000 images. Each label is 1 bit, and that constitutes about 100K of data volume that we're trying to model. Now, to avoid overfitting, the model should be smaller than the data itself. So we're limited to around 10 or 20,000 bits in our model because of that limited data size. That is not a big number when it comes to model complexity. Here's a new approach. The new approach, you forget about labels. Just don't worry about them. Or maybe you worry about them, but you think about them way after in the final phase of the procedure, in the final phase of the development. Instead of labels, and instead of modeling the label given image, you just model the images. You're just building big statistical models of the probability of an image. And the reason this is powerful is that now you have a vast data volume because you can use as many images as you want. You can go to the internet and scan the entire internet for images and just push them into your data pipeline. And not only that, but now each image is itself a rich data set. An image could be 1 million bits to describe. That means there's a lot to be learned from even a single image, and we have billions of them now. So now we have this colossally expanded data volume that we're building models for. And that's going to be important because these models are going to be very, very complex in the sense that they require many, many parameters. So here's a diagram for a neural network that has been built recently in a research lab. And what we're doing is each of these windows is a matrix of 1,000 or 10,000 parameters. And we're just stacking all of those layers one on top of each other. So each layer has multiple windows which represent convolutions, and each convolution can be 10,000, 20,000 parameters. And we're just stacking these up. So enormous numbers of parameters are going into building these models. And by the way, this diagram is actually pretty small compared to what the new models like GPT-4 are using. These new models using billions of parameters. Now, what's the point of building these gigantic models of the probability of an image? Why is this useful if our ultimate goal is to find cats or find pedestrians? Well, the point is that once you do this enormous training process on the image data set and build this enormous neural net, it will have all of those representations and concepts embedded into the network that will be learned automatically. So I just suggestively labeled here, maybe this window is a cat detector. Maybe this one next to it is a face detector. So whatever task we actually want to perform, we're going to reuse this model to perform it. Now, if you asked me 10 years ago, or even 5 years ago, Dan, isn't this reusability concept just your pet theory? I would have to say, yes, it's just my personal belief. It's my theory about what's going to happen. But now this theory has been totally vindicated because the LLM strategy is exactly the process I just described to you. So the LLM strategy, you're building a gigantic model of the probability of sentences. The difference is we're using text instead of images. You're training on an enormous database of text that you pulled from the internet. Your model is a deep neural network with billions and billions of parameters. And the point is that after you train it, it can be applied to all the text-related tasks. So there used to be this whole field called natural language processing that studied summarization and sentiment analysis and machine translation. And all of that is obsolete now because the LLM does all of those tasks automatically. So here's my belief and my theory about what should be done. You compile an enormous database of dash camera images, just images that the car sees as it's driving along. You build a gigantic model of the probability of one of these images. You represent it with a multi-billion parameter deep neural network. And the reason to do that is after you train it, this LDIM can be used for any driving task. It'll do face detection, it'll do pedestrian detection, lane detection, it will detect other cars, it will detect traffic signs. Friends, if we build this model, we can deploy real self-driving cars, and once they are widely deployed, they will save thousands of lives every year. I hope we can build this feature. Thank you very much.